Hello, welcome to part 3 of integration. This section is about using trigonometry to be able to, trigonometric rules to be able to integrate integrands that have trigonometric identities within them that you can't necessarily do straight away. Recap before we go on to this. We need to remember all of the trig that we've done before. Okay, I'm going to keep that over here, and it's going to be a tool that we're going to come to throughout this lesson. So, firstly, we should all remember, for example, that sine x over cos x is equal to tan x. A sine over cos is a tangerine. Okay, that's your first one. We also know our reciprocal functions. For example, we know cosec of x is 1 over sine of x. We know that sec of x is 1 over cos x. We know that cot x is 1 over tan x, or 1 over tan x, you can invert this fraction here, same as cos x over sine x. That's a starting point. Okay? So we've got all of them. Then we also know Pythagoras theorem. Sine squared of x plus cos squared of x is equal to 1. But we need to know the other two forms of that as well. So the first one, differentiate through by cos. Sine squared divided by cos squared, tan squared of x. Cos squared divided by cos squared, 1. 1 divided by cos squared, we've got sec squared of x. The other equation, divide through by sine. Sine squared divided by sine squared, 1. Cos squared divided by sine squared, cot. And 1 divided by sine, you've got cosec squared of x. So we have 3 more equations there. But it doesn't stop there, I'm afraid. We have to know more of them. Now, I'm not going to list the next bits, but you need to be aware of things like your sine a plus b, your addition formula, your cos a plus b, and to an extent, your tan a plus b. The main one is going to be cos a plus b. That's going to be the main one we're going to be using. But we know, for example, sine a plus b, we've got sine a cos b plus cos a sine b. Cos a plus b, you've got cos a cos b plus sine a sine b. Tan a plus b, you've got the whole fractional one that you don't need to remember off the top of your head, but tan a plus tan b over 1 minus tan a tan b. From then, we generate the double angle formula. So, sine 2 of a, we know is equal to 2 sine of a cos of a, because that was sine a plus sine a cos b, well, in this case it would be a and a. Sine a cos b, cos a plus cos a sine a. Two of them. The second one, cos of 2a. Again, using the cosine one, which was cos a cos b minus sine a sine b. We're going to have cos squared of a minus sine squared of a. Notice that I have swapped from x's to a's. It makes no difference, okay? But then we also can plug in the Pythagoras theorem to replace cos or sine. So the first one I can make cos 1 minus sine squared, which is going to leave us with 1 minus 2 sine squared of a. And if instead of replace the sine squared of a with 1 minus cos squared of a, that minus becomes positive, you get 2 cos squared of a minus 1. Okay. Super useful at first, okay? We've got pretty much all the information we need now in terms of trig, things we can draw on. There was also the other formula that you had in, that's given in the formula books, which is the way that we could split up in things into the sine p, sine q business. I might come on to that later on. Okay, so what we're going to look at is certain integrals that you can't do on their own. You have to employ one or some of these in order to do them. For example, if I was going to integrate tan squared of x, that is not an integral that we know. Okay. But we can have a look through our myriad of things here and see if there's a link. So we're looking at tan. We don't know how to integrate fractions as yet, so we're going to leave that one. Okay. Then we come across tan here. Tan squared plus 1 is equal to sec squared of x. We do know from the first standard lesson what the integral of sec squared is. The integral of sec squared is tan x. So therefore, I could rewrite this as tan squared is equal to sec squared of x minus 1 dx by taking away 1 from both sides. So, going through and integrating all of these, sec squared of x goes to tan x, and 1 goes to x, not forgetting r plus c. Okay, so we've used this identity. Okay, another example could be the integral of sine squared of x dx. And in fact, sine squared of x and cos squared of x as an integral are very similar questions. We don't use this one because we don't know how to integrate cos squared as it yet. Okay, they're going to be two separate ones. So we're not using any of these business, but we are going to use the double angle formulae for cos of A. Okay, I'm going to give you a rearranged form that will be useful here. I'm going to rearrange, you can see I've got a sine squared A and a cos squared A. I'm going to rearrange this equation here for sine squared of A. Okay, so I'll write out the work and then I'll erase it. So let's say I've got cos 2A is equal to the 1 minus 2 sine squared of A formula. First thing I can do, move the sine squared of A over here, move the cos 2A over here. So I've got 2 sine squared of A is equal to 1 minus cos 2 of A. Now, that means that sine squared of A is a half of 1 minus cos 2 of A. Now, cos 2 of A can be integrated directly because it's the example that we looked at in the second video for this, which is reverse chain rule. So, you get your setup there for sine squared of A. The other one is if I took the cos 2A being equal to 2 cos squared A minus 1. Well, I need to add 1 to both sides. So I'd have cos 2A plus 1 is equal to 2 cos squared of A, which means that cos squared of A on its own is equal to cos 2A plus 1 all divided by 2. And again, cos 2A, it's the same thing repeated. We've got two separate things. So what I'm going to do at this stage, I'm going to get rid of that working out so that we've just on this board got standard equations. Now, I'm not encouraging you to remember that these explicit formulae. Okay, what I am encouraging you to do though is remember how we use them, how we access them. Okay, sugar. Right, so now sine squared of x dx. I'm going to replace sine squared of x with a half load of the integral, or the integral out here to be known. This is the integral of a half 1 minus cos 2x dx. Little trick of the trade, if you've got a factor inside your entire integrand, you can take it out. So I'm going to take that half out. I'm going to have a half of the integral 1 minus cos 2x dx. I'm allowed to do it because this is a common factor. So now I've got a half of the integral of this is, well, 1 goes to x minus cos 2x, remember cos goes to sine, and I've got to divide by the differential of the inside, 2 plus c. Now, it doesn't matter when I multiply this half in at the end, whether or not I multiply c by a half or not, because c is just a constant that we can work out. So this could be x over 2 minus sine 2x over 4 plus some constant c. And there we have it. There we have what we needed to set up there. Okay? Similarly, not a question that's in the notes, but I will do it anyway. We can use a similar idea to do cos squared. Okay? So we'll just start with the squared of our normal trig functions that we're aware of. Okay? So let's say instead this time I did the integral of cos squared of x. Well, everything stays the same except for the thing that you substitute in, which looks ever so slightly different in this case. But the process of it is going to be pretty much identical. Cos squared of x, we worked out before, was a half of cos 2x plus 1. So now again, take the half out, cos 2x plus 1, which means I'm going to be multiplying through by the integral of this one is going to be sine 2x over 2 plus x. So I'm looking at sine 2x over 4 plus x over 2 plus c for cos 2x. So that's another situation, another setup where you can do using these two. Okay? So super useful for when you're doing sine squared or cos squared. You change up the cos 2a formula. When it's a tan squared, you change it into sec squared. Interestingly, if it were something like this, if it was the integral of, for example, 2 sine of x cos of x, hopefully you would spot something like that going, well, okay, that's the same as sine 2a. Which we now know we can integrate sine. Sine goes to minus cos, divide by the differential of the inside, plus c. But that can change. I could maybe have something like this. I could have, instead of a half, 2, I could have just sine x cos x. And hopefully you would spot that this is the same as having half of that. So that is the same as having a half of sine 2, that should be x. That should be x. I want to differentiate with respect to a. 2x dx, giving you the same thing when you deal with that on the outside. You're going to have minus cos of 2x divided by 2, but you've already got half of it, 4 plus c. And then, depending on what the number is here, you factorise that out. There is actually going to be another way of dealing with this sort of question. We will do it at a later lesson. Okay? So, a few other questions to think about here. Example 6, very similar. It says sine 3x cos 3x dx. That's very similar to what I've just done here. If I was to change this to match example 6, all I need to do is replace this with 3. Well, sine 3x cos 3x. You can see it is the form a half of the double sine, the angle we're looking at is 3, which means this is now a 6x. Everything else now stays the same. You're going to get a minus cos of 6x, but when you have a half and you're dividing here by 6, because that's your integral, your differential of the inside there, you can have 12 there. Okay? Looking exactly the same apart from that. Okay. Let's get rid of these ones. Okay, another one. This is part B of example 6. The integral of sec x plus tan x all squared dx. Now, if you were having a look at that and you weren't sure about what to do with it, you